In order to better understand the structure of the output layer, let's at first talk about the multi-class classification task. Let's have a look at the example of the dog breed classification task. So we want to predict the class, which is the number of the dog breed. Here you can see the 3 dog breeds: Dunker, Estonian Hound, and East Siberian Laika. So we want to predict the class label given the image, so given the pixel matrix. So for each image, we want to predict the class label. In this case, we have 3 objects, and we can unroll each matrix, so each image into the m-dimensional vector, and we'll get the feature matrix n by m. We want to predict the class labels with our multi-layered perceptron. So we want to get n by 1 column vector with these class labels. There are several reasons for why we can't just treat our class labels just like the ordinary numbers. Let's have a look at the example. So 2 images have classes 5 and 4, and here you can see that the number 5 is more than number 4, just because they're the ordinary numbers, and we want to map the image to its class label. And our multi-layered perceptron will consider this relationship between these 2 classes. But there is no connection between the class label and its value, its numeric value. So we should treat this in the other way, and the researchers proposed the method called one-hot encoding for this. In order to not to face the order relations problem, so in order to not to have the order relations between our class labels, we should use one-hot encoding method. So let's have a look at the example. We have 4 objects, and their labels are 0, 1, 2, and 0. And one-hot encoding states for the following algorithm. We put 1 only in that column that corresponds to the index of this class. So for the first object, we have the class label 0, and we put unit 1 in the first row in the column number 0. For the second object, we have the label 1, and we put 1 in the column number 1. For the third object, we have the class label number 2, and we put 1 in the column number 2. So for this object, we'll have the 1 in the column number 0. So this is the one-hot encoding. So we have one-hot encoded our labels. Now this is the matrix which looks like this. It's just n by k, where k equals to 3, because we have 3 classes here, 3 dog breeds. And we want to predict with our multi-layered perceptron these classes. So we want to train our network, and we should understand the structure of the output layer. The basic idea of the output layer of the multi-layered perceptron in the task of multi-class classification is as follows. We have k classes and k neurons. Here k equals to 3. So we have 3 neurons. Each neuron outputs the score of class 1, the score of class 2, and the score of class 3. Here we have 0, 1, and 2. So this output layer transforms the outputs of the previous hidden layers. So it's fully connected network. We must connect it with all the previous neurons. And here, the score of the Gth class states for the probability of the Gth class. So the score of the Gth neuron states for the probability of the Gth class. So this is the probability of class 0, probability of class 1, and probability of class 2. But this is not the probability itself, because in the output layer, these neurons don't have any activation function. It's just the linear transformation of the previous output of the previous hidden layer. And here we can have just numbers like 15, -2, 0.75, and this would be okay. But we want something that we can treat as a probability of a class. So we want to predict the probability of each class. Let's write the main features of the numbers which we can treat as a probability. There must be non-negative. They must be between 0 and 1, and the sum of this. If you want to just to model the distribution over the classes, we want these scores to sum in 1. We want the sum of the scores equals to 1. So we need some special transformation of our scores for them to be like probability distribution over our classes. And one that fits our goals is Softmax function. Let me rewrite previous result. Score 15, score -2, and score 0.75. And the Softmax function just scales our scores for them to be between 0 and 1, their sum to be 1 and to be equal to 1, and it makes our scores non-negative. Let's see. In the denominator we have the sum of the exponentials of every score, of each score. This is j to 1 to k 3. So for each class we just apply the exponential function to its score, and we will get this expression. For each score we can write according to the expression of Softmax function. So you can easily see that it makes our scores non-negative, and that now their sum would be equal to 1, because denominator is still the same and the numerator would be just like the denominator, and it will be 1 divided by 1. And it's between 0 and 1 because the maximum numerator that we can get is equal to the denominator. This is the Softmax activation. So let's summarize the structure of the output layer. The output layer consists of the k neurons, where k is the number of classes in our classification task. each neuron outputs its own score, and then after the output layer we apply the Softmax activation function. So if we have the input feature matrix n by m, after the output layer we would have n by k matrix, where each row consists of the probability distribution of the classes for the given object, for the object 0, for the object 1, and so on, and for the object number n. Here the number in this column number j states for the probability of the class j for this given object number 0. So our output layer has its own weight matrix, W out. It has the shape LR by K. K states for the number of classes, and LR is the number of neurons in the last hidden layer. So it's the number of neurons in the previous layer of the network, the layer that was before the output layer. And each of K neurons has LR weights, just like the ordinary hidden layer, but it outputs K numbers, K scores. So let's have a look at the full forward pass procedure. So this is the process when we apply all the transformations in our multi-layered perceptron to the input matrix. So we have the matrix n, which equals to 3 in that case, by m. So it's unsqueezed, unrolled pixels of each image. And then we apply the weight matrices of our hidden layers, one after another. Say our hidden layers. Its shape is m by m1, and so on, and l r-1 by lr. So lr neurons on the last hidden layer. Then we apply the weight matrix of the output layer. Here it states for the it equals some matrix of shape LR by K. K equals to 3 in that case because we have 3 dog breeds. And we get the matrix of shape N by K. So this is the row for each object, the row of let me say object number I. We have K numbers, so it's K-dimensional vector. Each number in this vector states for the score of this class. So 3 numbers, because K equals to 3 in this case. And then we apply Softmax activation for each row independently. And we get the matrix n by k, but here it stands not only for the score, it states for the so-called distribution, so-called probability distribution of the classes for this object. So for the object I, this number states for the probability distribution of the class 1, this of the class 2, and this number for the class 0, and this for every object. Remember that we have the one-hot encoded matrix with zeros and ones. And now we want to train our network to recognize the images. So we want our network to predict the correct classes. In order to train our network, we need the correct loss function. So for each object we have the true probability distribution. It is the vector of ones and zeros, and the predicted probability distribution. Let us say 0.7, 0.2, 0.1 after the softmax activation. And now we want to minimize the loss function. We want to minimize the difference between these two distributions. We want this to be 1, this to be 0, and this to be 0. So here we can use the cross-entropy loss. The name of the loss function you can see on the screen is the cross-entropy loss function. Let's have a look at the example to better understand this. Let us say we have 3 objects and 3 classes. And for each class there is the predicted probability distribution over the class labels. That's for object number 1, number 2, and so on. And this is the predicted, and we have the true labels. So it's the supervised learning task. We have true labels. Now we want to train our network. We want our predicted distribution for each object to match the true distribution for this object. So we want these rows to be equal. The cross-entropy loss allows us to reach this goal. So we can just use this formula, and let me write it like this. Multiplied by logarithm of 0.670 multiplied by logarithm of the (0.1) plus 0 multiplied by logarithm 0.23. This is for the first object, and plus just the same for the second object. Let's analyze this expression and understand why the cross-entropy helps us to predict the true distribution. So this is the logarithm function. And here you can see that logarithm applied to the value that is very close to 0. For example, here, here, here. Yeah, where it is just logarithm applied to 0, we can add some very low number. And for the numeric stability, here we have a -1 multiplier before our sum. Let's see on the graph that if we have this, we can just draw it like this if it is the minus logarithm applied to its argument. And here these components will produce large values of logarithm closer to 1 when we have a match a match between our classes, class distributions, predict distribution here and troop distribution here. And when we have a mismatch, we will have some very large negative numbers, and our loss will be very large. And here, in this case of the matched distributions, we will have very small loss values. So our goal is to minimize the loss, so to maximize this sum, to maximize these components, so to match between our true distribution and the predicted distribution.